So we're going to look at the gradient function. So we've done a fair bit on functions. If we're thinking about graphs, y equals function x, well, theoretically what it does is it measures how far above or below the x-axis the graph is, the y value. Well, the gradient function, which we use as a notation f dash x, measures how steep the graph is at that point. So it's measuring the slope. So, or another way of thinking about it is the rate that distance from the x-axis is changing. That is also known as the derivative. Okay, now at this stage, because we haven't obviously learned anything about calculus yet, we're going to use geometry to find the gradient function. Now we can do that for lines quite easily, because if you've got a horizontal line, well, a horizontal line, if we were to draw it, has a slope of 0. It doesn't matter where you are on the line. So I know if the function is a constant, well then that derivative must be 0. Now, if it's an oblique line, we know all oblique lines can be written as y equals mx plus b, but if that gradient function is measuring the slope, it's going to have a consistent value of m. Function is mx plus b, then the derivative would be m. So lines are fairly simple. Semicircle is another one we can do with the knowledge of coordinate geometry that we know already. So there's our standard semicircle. Square root of r squared minus x squared. Now, it doesn't have a constant slope, and it's changing as the x value changes. Now, if we talk about the slope of a curve, what we're really talking about is the slope of the tangent to the curve at that point that we're talking about. So I've put in a random point there, A, and there's the green tangent. So we're really saying, what's the slope of that line? Now, the point A would have coordinates, would have an x value, and then function x is the distance from the x-axis, so the y value is function x. But you may recall from circle geometry, we know the radius is perpendicular to the tangent at that point of contact. So I can find the slope of the tangent by, first of all, finding the slope of the radius. Rise over run, well, the rise is the function value, so function x, the run is the x value, so the slope of OA is function x on x, so therefore the slope of the tangent must be the negative inverse minus x on function x. So function x is the square root of r squared minus x squared, our semicircle. The derivative is, and all I've done here is actually substitute in the equation that we know. So it's minus x on the square root of r squared minus x squared. Okay, so that's semicircles. But that really restricts us. Lines, semicircles. There's obviously lots of other curves out there. So any other one, at this stage, we're going to estimate using secants around the point. So let's have a look at a quadratic function, which we know is a parabola. There's the point 2, 4. Now, how will I do it? I need 2 points to find the slope. So I'm going to pick 2 points either side of the one that we're interested in. So I've picked 1, 1 and 3, 9. We'll calculate the slope of that secant, and we'll use that as an estimate for the slope of the tangent. So in this case, I get 4. So I'm proposing that the function, or the derivative, or the gradient function, whichever you want to call it, at the point x equals 2 is 4. Now, how accurate my answer is going to be depends on how good my choice of the 2 points are. Because obviously if I picked a different 2 points, I'm probably going to get a different answer. Now, it turns out that that actually is correct. It does turn out to be 4. And the reason why is because I knew that in any parabola, if I pick symmetrically around the point, I'll get the exact value. So that's why I deliberately picked 1, 1 and 3, 9. They're both 1 unit either side of 2. So as long as I do that, I will get an exact answer for a quadratic. Well, if that's always true, let's try it out for this one I've drawn then. So I'm saying I've got x plus some value h and x minus some value h. So the y values would be x plus h squared and x minus h squared. Subbing that into our slope formula, I end up with 2x. So we're saying that the derivative is 2x, and that is indeed correct. All right, so that's fine for quadratics. Hyperbola, that's not going to work. There's a point 2.5. If I pick symmetrically either side, I've got the point 1, 1 and the point 3, 1/3. Okay, so I'm saying the slope is negative 1/3. Well, actually that's wrong. It's not. the actual slope there turns out to be -1/4. And perhaps you can see by eye, if you were to imagine drawing in the tangent at that green dot, it's not going to be parallel to that secant. So picking symmetrically either side of the point doesn't work for a hyperbola. The other thing about a graph like this, it's important the graph is continuous between the 2 points I pick. Because look at this choice. Imagine if I used BC. So C's on the other branch. Well, clearly that's not going to be a good estimate for our tangent. So it needs to be on the same branch. So, accurate graph for all these other functions. At this stage, there's no easy way around it other than just simply drawing the tangent in and then calculating its slope using rise over run. You know, read off your axes and what have you. Don't worry, we'll come up with a better way. But at this stage, that's probably the best way of doing it for other types of functions. So 9a, you'll notice in question 9 I've said, don't worry about the sketch. That'll make sense when you look at question 9, I think.